being here, the last talk of the last day of the whole session. So thank you for your courage. That's an empirical work here that I've been doing. So my main focus is actually on sparsity from frequentist analysis. This is work I've been doing during my, as a part-time job for companies in France during my years as a PhD student. So this work is a joint work with Julien, and so this is a work which was under the tutelage of Institut Bachelier. So for financial institutions, the French Deposit Fund and CNP Assurance, which is a huge insurance companies in France who have long-term asset allocation issues. So they were interested in conducting research focusing on long-term asset allocation. So based on the predictability assumption of asset returns. Okay. And we've been studying actually some Bayesian methods, tools, in order to model this predictability. So here I'm going to talk about the impacts of considering Bayesian point of view on predictability, what impacts would that have on the asset allocation, especially when you look at the risk of the assets. All right. So as for the agenda, so first of all, maybe you're not familiar with this literature in finance, empirical finance, about predictability, so I will talk about this. I will mention what we talk about. Then I will introduce the risk estimation, the imperfect predictor idea, in order to question the conventional wisdom about predictability. Basically, the conventional wisdom is that when you are an investor, the stocks they are considered as less volatile in the long-term horizon. So you are in pension fund, for instance, you want to invest in 30, 40 years. And basically, if you follow the conventional wisdom, you will invest more in stocks in the future because stocks are less volatile. And I will also introduce this part was mainly done by Julien, who developed a panel approach in order to use the cross-sectional information to gain in predictability, to obtain a gain in predictability. All right, so first of all, so when we talk about long-term analysis, first of all, we work with discrete time series, discrete time data. So there's nothing such as high-frequency data or intraday data. So we look at basically quarterly, so monthly, quarterly, or yearly data, okay? Which implies that actually there's a lack in a sufficiently large number of observations, which is a big issue, actually. So there is this distinctive property of a long-term analysis, which is that the risk premium, so the risk premium is the difference between your return and a risk-free asset, okay? So this appears, for instance, if you look at the Sharpe ratio. And actually, this risk premium varies over time, okay? Why does it vary? Because there are cycles in the markets. Those cycles, you can explain them by the monetary policies of the government, for instance. There are bubbles, switching regimes. If there are such cycles, actually, this implies that assets are actually predictable. There is a component among assets which is predictable. Because until the 60s and the 70s, basically the main model was a random walk model for the markets. Okay, so that means that if you just consider a linear relationship with an error and process, the slope parameter is equal to 1, actually. So the question is, how can we take advantage from predictability when we perform asset allocation? Okay. So nowadays, predictability, the existence of a statistically significant predictable component is accepted by the practitioners and people in the academic research. But the question is, how do we model this predictability? And so how does it impact the long-term asset allocation? And if we use this predictability, do we obtain a gain in terms of performance when performing asset allocation? So the seminal work is the one of Campbell and Viscera in 2001. So they developed an econometric framework to capture the predictability component. All right, so the standard modeling, so it's a simple model. Just consider an AR1 process, a VAR process. So when we model the predictability and the risk premium, we focus on the first order conditional moment. So we don't look at second order conditional moment, those kind of stuffs. We focus on the modeling of the conditional expectation. Okay? The conditional expectation, this one, condition on information at time t minus 1, we want the prediction of RT, the stock at time t. And what we do is, well, this expectation we construct, so we consider a linear projection over the space spanned by a set of predictors, xt. So if RT is a stock, usually xt contains the log dividend price ratio. Why? Because today, if the log dividend price ratio is low, it means future high returns in stocks. If RT is a bond, for instance, people in XT, they take the spread, so the difference between the long-term, the yield curve, the 10-year bond rate minus the short-term bond rate. So there's a significant literature which developed on this modeling and on the choice of the predictors in order to construct this relationship. And so predictability means that beta, the parameter, is statistically significant. Okay? So you just estimate this with the MLE or the OLS method, whatever, and if beta is statistically significant, then there is a predictable component in the stocks. All right, and once again, the choice of the right predictor is a major task in terms of interpretation, in terms of forecasting ability, and also there's this overfitting issue because you can add up many predictors inside of it, but because there is a lack of a significantly large number of observations, so definitely there is this overfitting issue at hand. All right, so the classic modeling for asset return predictability is a VAR model, vector autoregressive model. So basically we observe a stochastic process in discrete time, ZT. So we split it basically between the set of asset returns, so bonds, commodities, anything, and we have the set of predictors, so the log dividend price ratio, the spread, and so on. So the choice of them is motivated by economic research, financial research. All right, and so the VAR process is given by this process. Eta T is a strong white noise. It's a Gaussian white noise centered with this variance covariance sigma. And the estimation method is really simple, straightforward, OLS or MLE. But actually here there's a remark, an important one. I've mentioned we work with long-term data, so there is a low signal among the data. So the model complexity is in the order of pi square, which means that if P is inferior to T, so you can use the OLS estimator. Okay, so it works. You can draw meaningful conclusions out of the prediction results. If P is equal to T, you run the OLS, so you will get an R square, which is going to be equal to 1. However, if you look at the out-of-sample performance, you will perform really poorly. You will perform really poorly because your model captures not only the signal for which ZT-1 and the predictors should be used to predict the outcome, but it will also capture noise. Okay, so that means you cannot use it in order to make predictions. And it's even worse if P is superior to T, because there are more variables to estimate than observations. So that means if you look at the OLS estimator, it doesn't work because there is a rank condition which is not satisfied. So there is an identifiability issue. All right, so that's why the way to fix this lack of observations is, for instance, to consider a Bayesian point of view of the problem. Okay, so if you look at the OLS estimator, you can actually specify a prior over the parameter. If you take it as a Gaussian, you update it with the likelihood, and you obtain the ridge estimator, actually. And the ridge estimator is a way to fix this inversibility issue of the OLS estimator. And if you take, instead of a Gaussian, if you take a Laplace, so the distribution is more packed at the center, you're going to obtain the lasso estimator. So that's, there are people who worked on those topics, the Bayesian lasso things. All right, so this is all about sparsity, also sparsity analysis. So I close the parenthesis, but there's a huge literature in this. All right. And so the problem, as I mentioned, is that there are not so many observations, which means that the predictability relationship might not be stable, actually. So there is somehow a risk model and a parameter uncertainty, okay? And that's what we have used to take this uncertainty into account, to take this risk model into account. We use the Bayesian approach. And also, actually, if you are interested in international asset allocation, if you look at the predictability relationship among countries, there is actually a huge heterogeneity among countries. So that's why Julien, he worked on this panel approach to fix this issue in order to obtain a stable cross-sectional predictability relationship. And actually, this allows to increase the number of observations using this cross-sectional information. All right, so I will talk first about this, the modeling of predictability and how we introduce the risk estimation and the imperfect predictor into the predictability relationship. So to do so, we have developed a Bayesian analysis to account for this risk. And the main result is that actually the stocks, they are much less volatile in the long term. So this questions the conventional wisdom. And I will mention also this work developed by Julien, the panel approach, to fix actually the lack of data, so by increasing the number of observations through the countries. All right, so now I will mention what mean reversion is. So this is a consequence of predictability. Mean reversion basically means that in the long term, the assets are the volatility of the assets, the conditional volatility of the assets is decreasing. That's basically the idea of mean reversion. So if you take a bivariate VAR model, you have your return here, RT, you predict it with the, so if you take it as the stock, you predict it with the log dividend price ratio. The log dividend price ratio is an R1 process. The investors, they are interested in risk, of course, and they look at the cumulated risk of returns. Here is the two horizon variance of the cumulated returns. And based on this model, we have this decomposition of the risk, okay? The conditional variance. So those two terms, they positively contribute to the risk. But this one actually is a component which is called the mean reverting component. So this one depending on the sign of beta, of course, and of this correlation, negatively contributes in the variance. And generally, this beta in applications is positive, but this correlation is negative, actually. So this means that this one, once again, will negatively contribute in this variance, which means that we should observe in the long term volatility which decreases, which makes the asset more, attractive, actually. And also, this depends on the strength of this beta parameter, so on the strength of the predictability. All right, so if you extend it to the multivariate setting in the VAR, so at time t, I use all the information, I estimate the model, and based on the VAR model, we obtain this the risk term structure of the cumulated returns on the k horizon. So it's a very simple computation. And in practice, what we do is we estimate the parameters, and then we can plug it in this formula, and we obtain for each k horizon a profile of the risk, which is the main interest of investors, because it's the key input for asset allocation. And here is the main result, actually, of Campbell and Viscera. So it's based on American data until 2001. So using the VAR process that I've defined. So here is the conditional volatility. So here is the information you have at time t, and you look at the risk in 10 years, 20 years, and so on. And basically, what you observe is that the stocks is mean reverting. So it's less volatile in the long term. So it's more interesting if you're a pension fund to invest in stocks. So that's the conventional wisdom, actually. Conventional wisdom means that you should invest in stocks. And that's pretty much accepted by practitioners and academics until recently, actually. All right. However, if there's a way, I mean, it's quite reasonable to be skeptical about the predictability relationship, because basically there is a lack of observations. And quite often, when running a simple student test on the parameters, well, it's sometimes, depending on the data, of course, but it's quite often rejected. So there is not so much predictability relationship. So a way to integrate this uncertainty in the predictability relationship is to consider a Bayesian point of view. And the Bayesian point of view is that we will run integration with respect to the parameters. So the parameters, they are considered as random. So when considering the OLS estimation of the VAR process, so written here in the compact way, we obtain the classic OLS estimator. So under the assumption that this guy, the design matrix, is inversible. We obtain also an estimate of the variance covariance matrix. And if we want to run parameter integration, we use those guys in order to compute posterior distributions with respect to these components here. So what we did is that we used, so to introduce parameter uncertainty, we specified diffuse priors with respect to C and sigma, and the posterior distribution is computed using those distributions. So this enables us to simulate, to integrate with respect to those parameters, phi 0 and phi 1. So this is a way to be skeptical about predictability. And here is the impact on the volatility profile for French data of integrating parameter uncertainty in the predictability relationship. So this is for French data, so based on the MSCI index from 1970 to 2015. So this is the volatility in black for the return using the VAR model, but from a frequentist point of view. And in the dashed line is the integration of parameter uncertainty, so using the Bayesian integration. And basically, we observed that, so for the black line, actually, the stock, the volatility is pretty flat, so there is not so much mean reversion. But if you take the parameter uncertainty into account, well, the volatility of stocks is much bigger in the long term, which makes stocks much less attractive, actually, which is not that much case for the cash. So it's a short-term investment rate. And for the bond, there is a little difference in the long-term horizon, but not the case, definitely not the case for stocks. All right. So that's for integrating parameter uncertainty into account. And so far, what I've shown, sorry, to plot those risk profiles is that we've computed this variance over there. However, if we want to be even more skeptical in the predictability relationship, we can assume that, and we should actually take into account the fact that we miss some information in the linear relationship. So we are going to add to the parameter uncertainty the omitted variable bias. So to do so, by integrating this omitted variable bias, this means that phi 0 and phi 1 actually do not entirely reflect the predictability relationship. We actually extend the framework of Pastor-Estambo in order to take both parameter uncertainty and the omitted variable bias into account. So to do so, we have considered a state space model. So the state space model is modeled with this system over there. So RT, once again, is the stocks. XT is the vector of predictors. And pi t is a latent process, so it's not observed. And this guy over there reflects the fact that the linear relationship, when we model this linear relationship, we're missing information. So we are even more skeptical in the predictability relationship. And this latent process is modeled with this AR1 dynamic. And the noises are supposed to be jointly normally distributed. And the key components are the correlation between UT and MUT, and also the variance of this latent process. Because the variance somehow determines how imperfect this linear relationship is, and this reflects also how uncertain the future trajectory of pi t is in the long term. All right, so the predictive system is estimated based on a Bayesian approach. So the Bayesian approach is actually pretty nice because this allows to specify some priors on the parameters. And those priors, they are economically and financially justified. So it makes sense to define such distribution in respect to such parameter based, for instance, on the future economic growth or the future rates defined by the central bank, for instance. So it's pretty nice to use this Bayesian approach. And there's a difficulty also for estimating such model is that the pi t process is latent, so it's not directly observed. So in order to estimate this model, we have applied forward filtering, backward sampling algorithm. So in the forward filtering, there is an evolution step which requires the estimation of the conditional moments of the latent process. So we use the Kalman filter to do so. And the Kalman filter works because of the assumption on those noises. And in the backward sampling, we simulate the whole joint distribution based on whole observations, actually. So that's what here basically I mentioned. We need to compute the conditional expectation of those guys over there. So we use the Kalman filtering. And for the parameters, we have performed Bayesian integration. So we both model parameter uncertainty and the omitted variable bias. So meaning that the predictors xt, they are not perfect to capture the whole predictability relationship. So for the parameters, there is one important parameter, which is the variance of the latent process, the variance of this guy. And to do so, we have considered such prior for this variance. So it depends on T0 is an hypothetical sample size of the latent process. And one should calibrate sigma 0, this one. So the calibration depends on the on financial studies. Also, it's motivated by financial studies. So it's based on the pension funds' belief about the future uncertainty. So once again, the Bayesian approach is pretty nice because it allows to calibrate such quantities based on practice. Because investors are interested, once again, in the computation of this variance, using probability simple computation, this variance can be decomposed in those two terms. So the first component is the volatility computed and plotted in here, actually. So that's this volatility. So this is this first term here. But if you believe that your predictors, they are imperfect to capture the predictability relationship, you should take this second term into account. So that's the conditional variance with respect to this expectation here. And if you believe that, once again, the var process and the predictors are imperfect to predict the returns, you should take this quantity into account. And of course, this will positively contribute in the long-term volatility. All right, and so here is the impact of the sigma 0 prior that you have on the calibration of this sigma 0. So basically, for quarterly stock returns, this guy, the volatility is around 10%, 8-10%. And so here is the risk term structure for the French stock returns, for quarterly French stock returns. And of course, the volatility increases depending on the choice, on the calibration of the variance. So once again, this is the choice of the pension fund or the financial institution. But interestingly is this result. This result depicts the risk term structure for different point of views. This guy here is the variance. So this is, sorry, so this is the conditional volatility for French stocks using only the log dividend price ratio to predict it. Okay. So this guy is the conditional volatility if I have a frequentist approach. Okay. The blue one is when I take parameter uncertainty into account. So I've performed Bayesian integration. And this one is when I take both parameter uncertainty and imperfect predictors into account. So I take the latent process into account. And basically, if you take this variance into account, well, in the long term, stocks are not attractive at all, actually. So this, of course, this definitely exaggerates the volatility in the long term of returns. So there is a much deeper work to be done on the calibration of this sigma prior. So this is why we discuss with the financial institution to talk about how we should choose those guys over there. But this is a nice plot because this shows that actually you should take this risk into account. This is a risk model that should be taken into account. All right, and so here I'm going to mention the panel approach, which was developed by so both of us who work on it, but Julien devised the model, and he made most of the empirical applications. So here the idea is how can we use the cross-sectional information in order to gain precision in the predictability relationship. So to do so, the idea is that for each individual countries, you consider the same linear relationship as previously reported, but for each country. So this is, for instance, the stocks for France, and here is the log dividend price ratio for France. And each equation follows a sure, so similarly unrelated relationship. So actually the estimation can be performed equation by equation, but because the innovations, they are correlated, so there's an efficiency in terms of variance. And in this panel approach, we actually consider the parameters alpha and beta to be random variables, where the data generating process of each country corresponds to a random draw from the cross-section of return processes. So we'll define what this is, this cross-section. So this is based basically on the exchangeability assumption. So there was a talk which mentioned this idea yesterday. So basically, if you have the UK stock return, the US stock return, the exchangeability refers to the fact that each parameter can be simulated in this distribution, where we have a common mean, the cross-sectional common mean, and the cross-sectional common variance over there. So that's the exchangeability assumption. So I will give now the intuition of exchangeability with those slides here. If we assume, so once again, the parameters, they are supposed to be random. If we assume non-informative priors with respect to those parameters, so basically we have those distribution over there, right? But now if we assume that we know about the cross-sectional common mean of the returns, then we consider this distribution. If we assume that, well, we don't really know about individual countries, so it would make sense to consider those conditional distribution of each parameters. So the distribution now, of course, changes because of this assumption over there. And now if we assume that we observe the data from the UK, for instance, then the posterior distribution should be updated because we observe the UK data. So the posterior distribution is shifted now. And the question is, how can we take this information into account in the cross-section? And so if we assume that we observe the UK data, so that means we can obtain a more precise posterior respect to the UK beta parameter using the cross-sectional information. So we have an updated posterior distribution with respect to the observation in the UK and the cross-sectional beta parameter. So the distribution now is shifted once again compared to previously. Okay. And so the same applies for the US data. So we observe the US data, so we can update the posterior distribution. And there is the shift in this distribution of the beta US parameter. And basically, there is a learning scheme here. So you observe the data for each country. You use the cross-sectional information. Basically, you update all posteriors, all posterior distributions until convergence to the steady state, condition. All right. So that's for the exchangeability intuition. As for the predictive system, we have considered this seemingly unrelated relationship where this country-level prediction can be summarized in this YT vector. And so we assume a sure seemingly unrelated model for both returns and predictors. And the parameter of interest is phi. So it contains the predictability relationship. And to do so, we specify some priors with respect to these phi parameters. And the prior is specified as follows. Okay? So basically each country, each posterior distribution for each country's parameter will be shrunk toward the common mean, actually. And there's also a prior respect to this nuisance parameter. So it's an idiosyncratic parameter, basically, which should be simulated so that there is a stationarity condition which should be satisfied. And we also assume diffuse priors with respect to the common mean and with respect to this delta parameter and the variance covariance matrix, sigma. And basically what we obtain is using this exchangeability assumption and this econometric model, we obtain a stable predictability relationship across countries. So here is the posterior distribution. Is the average equity premium obtained thanks to the posterior distribution of the parameters. And so in the line over there, it's the median of the posterior distribution. We have the quartiles over there, and the whiskers represents the 95% set of credibility. And in diamonds, we have the sample equity premium. So if you just look at the diamonds, there is a heterogeneity through countries. And so basically, this would mean that, well, there is not so much information to take out of it because of this heterogeneity. However, if you apply the exchangeability assumption with the priors that I've provided, we obtain a much more stable predictability relationship among countries. So that means we can make use of this information. But I don't really have time to present the asset allocation results, but if you are if you want to have a diversified portfolio allocation, so you look at international asset allocations, and we basically obtain much more stable asset allocation weights among countries. All right, so for the concluding remarks, I've mentioned that the main issue of this long-term asset allocation is that we work with low signal data, and there are not so many observations. So that's why parameter uncertainty allows to be skeptical in the predictability relationship, meaning that actually stocks and actually a broad range of assets, they are considered as being much more volatile in the long term. And the panel approach is pretty nice because it allows to use the cross-sectional information. So basically, you can increase the sample size in order to obtain a stable predictability relationship. So for the further research, so of course extending the panel approach to a broader range of assets and predictors. And also there is this sparse modeling. So using here the frequentist approach, not a Bayesian point of view, or using also factor modeling. Factor modeling, which can be a way to reduce the dimensionality issue. All right, so I finished. If you've got some questions, let me know. Yeah.
So you mentioned in the first algorithm that you use Kalman filtering?
Yeah, Kalman filtering in FFBS method.
So is this part of the MCMC scheme? Or
Yes, it's an MCMC scheme.
so do you still get the exact posterior, or this Kalman filter is an approximation?
It's an approximation, this Kalman filter. It's an approximation.